Unit 3.1 derivatives of polynomials and exponential functions. There is a constant rule, and that constant rule is pretty much what we need for 3.1, and it is a statement. So if c is a real number, then d of x equals 0. So prove this rule correct by just a simple graph. So if we have a line right here, and we say y equals c, then we know the slope of a line is 0, which comes out to be the same thing as dd of x equals to 0. These examples, we just see that these are practically just constant numbers, so it's just simply the constant rule, which would end up being 0. But when we're given a graph or a function right here in this case, we can tell that all in the graph the slope is 0. So in that case, we can easily tell that the derivative of x equals 1. So the power rule is also another main rule that we have in derivatives of polynomials and exponential functions. And simply you just multiply your exponent to your coefficient, in this case being magical 1, which becomes a 4, and you subtract a 1 from your exponent, which becomes a 3, and that is right there. Now for 3.2, there are two important rules. They're known as the product rule and the quotient rule. But right now we'll be doing the product rule, and it pretty simply just states when you have two functions such as f of x and g of x, and they're being multiplied, the rule that you use would just be find the derivative of f of x times g of x plus regular f of x times the derivative of g of x. Here I have an example for the product rule, and I have two functions, f of x and g of x, and we're just gonna solve it out just to show product rule. So we're gonna get the derivative of our f of x, which is 2x, times our g of x plus the f of x plus times the derivative of our g of x, which comes out to be, and then we should multiply each one. This one comes out to be 2 to the fourth, 8x plus 3x to the fourth. Then we add the terms again. 8x. Another essential rule in the quotient and product rule, which is unit 3.2, is the quotient rule, which states when dividing two functions such as f of x divided by g of x, your function comes out to be your f or g of x times the derivative of your f of x minus your f of x times the derivative of your g of x all over your g of x squared. So for the quotient rule example, I'll just be demonstrating how to just put it together, and it's just simply using the two functions. So we always start off with the bottom one, so it would be x to the fifth plus x times the derivative of f of x, which would be 2x minus f of x times the derivative of g of x all over g of x squared. There it is. Now jumping into unit 3.4 derivatives of trig functions, I will be writing down some statements that are pretty useful when solving. So we have sine of x equals cosine of x, cosine of x equals negative sine of x, tangent of x equals secant squared of x, secant equals plus tangent x, cosecant x equals negative cosecant x times cotangent x, and lastly cotangent x equals negative cosecant squared x. Right here, so f of x equals sine squared x. And for this one, we can actually use the chain rule, which I will be speaking on unit 3.5, which is the next one. And the chain rule states that we can bring this to up front, so it would be something like this, and then our derivative of sine is cosine, so pretty much like this, and that is our answer. So for unit 3.5, it's the chain rule, and right here the chain rule, I have the rule written down, which dy d of x equals to the derivative of the outside function, leaving the inside alone, times the derivative of the inside function, and that pretty much settles that. Here I have an example for the chain rule, and the function is dy d of x equals 3x plus 1 to the 7th. So we're going to get the derivative of the outside, leaving the inside first alone. So we're going to multiply our constant, which is 7, and then 3x plus 1. Subtract the 1, becomes 6. But we can't forget our inside also has a derivative, so we also have to get that. So, but we would have to multiply that with this whole thing right here. So what we're going to do is rewrite this right here. And then we're going to get the derivative of this. It would be 3, and then the derivative of 1 is 0 because of the constant rule. So it would be 3, and you pretty much just multiply this to your front number, and it becomes 21 to the 3x plus 1 to the 6. So for unit 3.6, implicit differentiation, just a solid point is to be able to differentiate both sides of the function with respect to x. So here for implicit differentiation, I have an example to find dy dx of the function. So first we want to start off by differentiating both sides. So it means by getting the derivative. So for the x squared would be 2x, and then for the y would be 2y. But since we have a y, we know we have to add a dy dx, which is needed to find dy dx, and then equals 36. But since we know 36 is a constant, it's actually 0. So now we want to get dy dx alone, and to do that we have to subtract the 2x to this side. So now we have 2y dy dx equals negative 2x. And then to get the dy dx alone, we have to now divide by the 2y. Then we have 2y, and then dy dx equals negative 2x over 2y. But even then, we can still simplify these 2's, make it more simple. So dy dx equals to negative x over y. So here's a simply slightly challenging, a little bit more difficult problem for implicit differentiation. So when finding this, we can find the derivative of sine x, as we should know from the trig, is cosine x. And then for this part, we can use the product rule, which comes out to be our f of x, which would be x squared, times the derivative of our g of x, which is our y, but in implicit differentiation, we're going to need the dy dx plus the derivative of the f of x, which would be 2x, plus just times our just simple f of x would be y. And then plus our dy d of x, which is our derivative of our y back here. And then just simply equals to 10, since this is our coefficient, and the derivative of our coefficient would be just 10. From there, now we can distribute our negative, since we have our product rule in parentheses. So we're going to distribute our negative. So come out to the cosine x, negative x squared, dy d of x minus 2xy plus dy d of x equals 10. And then from there, we can change some things to the other side by just subtracting cosine x and adding 2xy, which comes out to dy d of x plus dy d of x. Oh, and I forgot my x squared. And then is equal to 10 minus cosine x plus 2xy. And then from there, we can actually factor this out. So it would be dy d of x minus x squared plus 1 equals 10 minus cosine x plus 2xy. And then, we want to get our dy d of x alone, so we're just going to simply divide, bring it to the other side, cancels out. So then our final answer for dy d of x would be 10 minus cosine x plus 2xy all over negative x squared plus 1. And that is how you differentiate implicit problems. So here for higher derivatives, I have a little bit more complicated problem than the last one, and it's 3 square root x plus 5x. So a good thing to remember is that square root x is also equal to x to the 1/2. Just makes more things simple in the long run. So when finding the first derivative, we are going to multiply our 1/2 times 3, making it 3/2 x, and then it becomes negative 1/2 plus the derivative of 5x is 5. So finding the second derivative, we multiply the negative 1/2, making it a negative times the 3/2, and then that becomes to negative 3/4 x to the negative 3/2. And then the derivative of this, it's coefficient rule, so it's no longer there. So we just end up with these two. So when taking the third derivative, our two negatives are going to result in a positive fraction, which is going to be 9/8 x. And then our exponent is once reduced again to negative 5/2. And then I'll stop there, but you can keep going. This will just be reducing, and you'll keep multiplying your coefficient once again. And yeah. So for 3.8 derivatives of logarithmic functions, there's four principal formulas that I'll be reviewing and doing some examples. But the first one is pretty simple. dd of x says that the ln